Welcome back to Engineering Dynamics. I'm your host, Dr. Walk. Today we're going to be going over rigid body motion again. This time we are going to look at another technique to solve these complex motions. And this technique is called the instantaneous center. And what it does is it takes a planar motion and it converts it into pure rotation. It does that by finding some point that is on or off the body that actually has zero translational velocity. So it takes an equation that looks like VA equals VB plus omega cross RA with respect to B. And basically what it does is it says that's zero. In order to do this, there are there's three techniques to find where that point is. The first way is just visually by doing it. Okay, so let's take this for example. If I'm just looking at this rigid body right here, where on this rigid body would it be zero linear velocity? Now, a lot of students will say, oh, the center has zero. That's not correct because the center is still moving. It's actually going to be in contact with the floor. This is where velocity equals zero. So if I wanted to describe the velocity of A, B, and C, I could do relative motion, and I could say that VA equals VB plus omega, and this is of a disk, so let's just call this omega D. Omega D cross RA with respect to B. I could also, though, because maybe I'm only given this, and I don't know what this is, and I can measure this, but I mean, that doesn't really simplify the problem at all. But if I do, let's call this G. If I said VA equals VG plus omega D cross RA with respect to B, the problem becomes much more simple, right? So now we can take one of those unknowns out. Okay, so that's one way of doing it is by just looking at it. So another way is going to be using perpendiculars. So what do I mean by that? Let's look at an example. Okay, so let's take a look at this rigid body, and I put what you need to do in order to draw perpendiculars is you have to say, okay, we know, because in order to make this true, we need to draw the position vector and we need to draw the velocity vector. So here I drew, because you do have to know a couple of things. You will know the direction of your velocity. So I went ahead and I drew those in, but now I have to find the point. In order to find the point, I'm going to draw perpendiculars. Okay, so what I'm going to do is I'm going to draw a perpendicular line here and a perpendicular line here. I'm doing perpendiculars because we know that our position vector, it has to be perpendicular to velocity. So if this is the velocity of B and this is the velocity of A, I know that I am going to have a position vector perpendicular to it. And I'm going to extend it both ways because I have no idea if the position from B to my point of no rotation is down here or if it's up here. And I'm going to do the same thing with this one. Okay, and wherever they intersect right here is going to be what we call the IC. And at this point, that is not going to rotate. It is saying that A and B are in pure rotation about this point, about the IC. That's the whole definition of instantaneous center. At one instant during the mechanism's rotation, a random point is going to have zero velocity. So at one point, that whole mechanism is going to rotate about it. It's going to be its own axis. Okay, so when we learn pure rotation about an axis, we said all of the points that are not on the axis are going to rotate in the same angular velocity. That's the same thing here, except our axis is now going to be that IC. So one way to find it is like this. And then another example is going to be if the points, so what happens if the points are, oops, I did not get this. So let's take a look at this one. So this time, if I draw a perpendicular, it doesn't really do much, right? So I'm going to have to make up one more rule here. So the first thing I'm going to do is draw a perpendicular line on the butt. But if the velocity vectors are here, A and B, what I'm going to have to do is do one more connection, and I'm just going to connect the heads. So I'm going to draw a line that connects the heads, and wherever it connects is the point of rotation. And then there's one other example. We'll do it here. And what if I said that A and B have the same velocity? What would you say? Well, by inspection, I would say this is in pure translation, so there's not going to be an IC. But if you didn't know that, you could connect the tails, right? Like you make your perpendicular, imagine that's a straight line. And then you also connect the heads, and that's a straight line, use your imagination. It's not going to rotate. It's just going to be in pure translation. So those are some common ones. There's one more common case that I want to show you. And it's if the vectors are going in opposite directions. So let's take a look at this case. Again, I'm going to draw the perpendiculars. Oh my goodness, I'm so bad at this. Let me try with a pen. That was with my mouse. Maybe my pen will be better. Not much, but okay, I'll take it. So we're going to draw the perpendiculars, and then we're also going to connect the heads. So my IC is now going to be somewhere in the middle. And then if you have to find the actual value, which we're going to find in examples, you can use similar triangles. Like this would be a similar triangle to this. Okay, so let's just practice identifying where the IC is. So let me draw a few things. So what if I said here is a bar A, B, and B is also connected to a bar BC, and C is connected to D. So my first question is what type of motion is rigid body AB undergoing? Pure rotation about A. So pure rotation about A. And what is bar BC doing? BC is going to be doing planar, and CD is also going to be pure rotation. C is pure rotation about D. So I can say, in order to solve a velocity of B, I can just say that the velocity of B is equal to omega cross RB with respect to A. That's what that means. And then for VC is simply omega CD cross RC with respect to D, and this omega is AB. But this guy here is going to be V, either VC or B, it doesn't matter, would equal VB plus omega BC cross RC with respect to B. So this is more complicated. In order to get rid of the B, what we can do is we can take out that section of rigid body. So we have C and B. And the first thing we have to do is locate our velocity vectors. If B is in pure rotation about A, there's a circle here, right? And so we know that it's going to be tangent to the curve. So B, its rotation is going to be tangent to that curve. So it's either going to be going up or down. I'm not really sure what, but it's up or down. So this could be VB or this could be VB. This is also going in a circle. So its velocity would be either that way or that way. So our job is to say, okay, where do these connect, right? Where do these connect? We have to draw our position vectors. So our position vector says at the tail of the velocity vector, we have to draw a perpendicular position vector. So that's going to be one position vector. Here is the tail of my velocity vector. It's going to be perpendicular. So for this rigid body, this is now IC. So now I can take one planar equation and I can represent it in two pure rotational equations. So I can say that VC is equal to omega BC cross RC with respect to IC. And I can say that VB is equal to omega BC cross RB with respect to IC. So just by locating that instantaneous center, I can take a really complex equation. So I can take this really complex equation and I can simplify into two simple equations. Okay, so that was one example. Can you guys tell me where the IC is on this one? If I asked you, where's the IC of the pulley? Where would you say? Again, a lot of students go for this point. It's not. It's actually going to be right here. And think about it. Think about the example we did before of a wheel. That was in my previous video. But look at, if you take this and you just turn it, it's rolling down a street. It's like it's rolling down a street. So really your IC is going to be there. Okay?